Hello everyone, and welcome to the M2L31 series Level 1 training course. In this video, we're going to take a look at an example program for Low Power GPIO. We'll show you how, in low power mode, the hardware can automatically control an LED using auto operation mode, achieving a low power yet stable operation. You can download the example program from the link in the video description below. Once you've downloaded it, just extract the files and open the project in the GPIO development environment, following the provided path. This example program uses the NuMicro M2L31 SG development board. It mainly demonstrates how to make the red and green LED blink while the system is in power down mode. The program also uses an add-on board called the M2L31 Learning Board, which has red and green LEDs. The corresponding pins for these LEDs are PB0 and PB1. If you want to connect your computer to the development board to monitor the output messages, make sure to enable the virtual COM port on the right side of the board. Specifically, turn on the TXD and RXD switches. As shown in the diagram, just slide both switches to the right. This way, your computer will be able to properly receive the messages sent from the development board. Let's quickly go over the overall flow of this example program. First, we use a low-power timer to trigger low-power PDMA channel 0 every 500 milliseconds. Once the PDMA is triggered, it automatically transfers the pre-stored pattern data from low-power SRAM to the low-power GPIO. This allows the LED to blink according to the pattern, without the CPU needing to be constantly involved. At the same time, we've configured it so that the CPU is only awakened once via an interrupt after the PDMA transfer is completed. Next, let's take a look at how the peripherals interact through the bus matrix. In this system, the CPU bus acts as the master, able to read from or write to resources in the low-power domain. Within the low-power domain, the low-power PDMA also acts as a master. It can directly read data from low-power SRAM and write it to the low-power GPIO. This means that even when the CPU is in sleep mode, the low-power PDMA can independently handle data transfers and control the I/O. Next, let's go over the program structure. If we start from the main function, we can see the overall flow of the code. In this low-power GPIO example, we actually don't use many features. The main modules involved are the low-power timer, the low-power GPIO itself, and the low-power PDMA. These modules work together to achieve automatic control while the system is in low-power mode. As for the initial system setup, such as the minimum current init function, system init function, and UART init function, you can refer to the previous low-power timer sample code video for detailed explanations. Let's first take a look at the timer configuration. Here, we set the low-power timer to operate in periodic mode, which means it counts every 500 milliseconds. Each time the timer completes a count, it automatically triggers the low-power PDMA, so the subsequent data transfer can proceed on its own without any CPU involvement. Next, let's look at the LED pin configuration. We set both the green and red LED pins as outputs for the low-power GPIO, and make sure they are mapped to the correct pins. One important point to remember is to enable the setting that allows the low-power PDMA to access the low-power GPIO. This ensures that the data can be automatically controlled and output by the hardware later on. Next, let's talk about the low-power PDMA setup. In this example, we set the transfer width to 32 bits, and we're sending a total of 10 data items. The data transfer direction is from a source array stored in low-power SRAM straight to the data out register of the low-power GPIO, which directly controls the output state of the LED. It's also important to configure the trigger source for the PDMA. Here, we use low-power timer 0, so each PDMA transfer is triggered periodically by the timer. Finally, let's take a look at how the program actually runs. Once all the initialization and configuration are complete, the program first prepares 10 data items and stores them in the source array in low-power SRAM. Then, the system enters NPD3 mode and enables the auto-operation mode of the low-power GPIO. Inside the loop, the low-power PDMA continuously transfers the data to the low-power GPIO, allowing the LED to blink according to the defined pattern. The CPU is only woken up under the specified conditions. This way, the system can maintain low-power operation most of the time. So what exactly are these 10 data items? It's actually quite simple. From the code, you can see that we fill the corresponding GPIO output registers with either high or low values. This directly controls the output state of the low-power GPIO, which in turn determines whether each LED is on or off. Next, let's flash the program onto the board and take a look at how this demo actually runs. Now you can open the Kyle project file from the path we mentioned earlier. Next, click Build to compile the project. Once the compilation is complete, connect the development board to your PC via the debugger's USB port. Then click Download to flash the program onto the board. After the program is successfully uploaded, you'll see the red and green LED blinking on the board. You can also open a serial communication tool at the same time and make sure the TX switch on the development board is turned on, as we mentioned earlier, so you can view the UART messages. Next, let's use the current measurement software to check the system's actual power consumption. From the measurement results, you'll see that since the CPU doesn't need to be continuously woken up in this scenario, the overall average current consumption is only about 18 microamps. With this program flow, we can actually observe the system behavior directly during current measurement. Looking at the LED GPIO output waveform below, you can see the high and low transitions, which correspond to the LED turning on and off, creating the blinking effect. Each current peak represents a moment when the CPU is awakened. This happens right after the PDMA completes a data transfer. The CPU wakes up, executes the loop, and then returns to power down mode. You can also try modifying the LED blinking pattern or increasing the number of data entries to see how the wake-up events and low-power behavior change. That wraps up our introduction to the low-power GPIO sample code in this training session. Thank you for watching, and if you'd like to learn more, please feel free to reach out to us.